Yes, welcome everyone to GeoHug. So before we kick off today's session, I'd just like to take this time to acknowledge the traditional lands which we're all coming from today. I'm here on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present, and future. So I'm thrilled to have Adam Simon joining us today. Adam is the Arthur F. Now Professor of Earth and Environmental Sciences at the University of Michigan. So his research program combines field, analytical, and experimental work to unravel the genesis of mineral systems, including IOCG, IOA, porphyry, and Carlin systems. He's co-authored 2 textbooks and has published nearly 50 papers in the field of mineral resources. So with his expertise, it is going to be awesome to learn from him today about why the genetic models for IOCG and IOA deposits are so controversial. So it is going to be an unreal session. I hope you all enjoy it. Please use the chat. You'll have the chance to jump off mute and we'll be opening up the floor at the end. And yes, thank you so much, Adam, for joining. It's amazing having you.
All right, so here's what I want to do today. I want to tell everybody that iron oxide apatite and iron oxide copper gold deposits are genetically related to each other, but they don't form at exactly the same time. And I want to make the point that they are more simple than we have thought over the last several decades. And that's going to get to my final remarks about why they're so controversial. So I dropped the 2 links on the bottom right here into the chat so everybody can take a look at this. And I'll just highlight this. I put my entire natural resources, economics, and the environment course online. So these were all high definition video recordings I made during the COVID pandemic, and I'm happy for people to use them if you want. I also want to say that the work I'll present today is highly collaborative. So I've had the pleasure of working with a lot of PhD students at the University of Maryland and the University of Michigan, and the University of Chile, and then several faculty members up here who have added significant value to our research. Any mistakes are my own. So what do we know? We know that iron oxide copper gold and iron oxide apatite deposits have formed on all of the 6 continents where we have been able to do discovery. And certainly they exist on Antarctica, but they're currently buried under ice. If we look around the world, we can see on average for most districts that host IOCG and IOA deposits, they are contemporaneous with subduction zone systems, but not in all cases. There is still controversy about whether or not the IOCG and IOA deposits here in the United States and Missouri, whether they formed contemporaneously with a subduction zone environment. And then there's also a lot of controversy here in the Cloncurry district in Queensland as to what the exact tectonic environment was at the time that IOCG and IOA deposits formed. We know that both of these deposit types have formed throughout geologic time. So this is a plot with age on the y-axis and reported resource in millions of tons on the x-axis. And all I want you to see here is the colored diamonds are for copper and the empty are for iron. So the empty represent iron oxide apatite deposits and the filled represent iron oxide copper gold deposits. And you can see that they have formed going back as far as the early Proterozoic into the late Archean all the way through to today. So whatever processes result in the formation of IOCG and IOA deposits, they were operating at least several billion years ago before the great oxidation event that led to the increase of oxygen in the atmosphere and increase of oxygen in the oceans. We, meaning my group and my collaborators, have spent most of the last 10 years focused on IOCG and IOA deposits in the Andean arc. The map on the right shows you one of the deposits we've spent a lot of time working on, Mina Justa, which has been the dissertation topic for Maria Alejandra Rodriguez Mustafa, who defends her dissertation on Friday. And we've had a number of other PhD students work on deposits here in what we call the Chilean Iron Belt. And what I want your eyes to see, the most important thing here, is that everything in orange, the squares, those are IOCG deposits. And everything that is a green little house symbol, that's an iron oxide apatite deposit. So when we look at districts that host IOCG and IOA deposits, there is a clear spatial association between both deposit types. And we suggest that there is a temporal relationship and a genetic relationship between them as well. People such as Jeremy Richards, who tragically passed away a couple of years ago, have spent a lot of time also trying to understand the evolution of IOCG and IOA deposits. And this is a slide I borrowed from a paper that he published in 2017. And all I want to do here is plant the teaser that when we look at the Chilean iron belt, we see lots of IOCG and iron oxide apatite deposits, and we see lots of porphyry copper moly gold deposits. And then we see some deposits, for example, Productora, that have characteristics of both porphyry and IOCG systems. And what you can see here on this map from Jeremy's paper is that if we look at the ages, there is a broad overlap in the time of formation between some of the IOCG and some of the porphyry systems. And I'll come back and tell you why I think that's important. If we look specifically at the Chilean iron belt, you can read the text on the left and listen to my voice. If we look at the three cartoons from top to bottom, what we know very well about the evolution of IOCG and IOA deposits in the Chilean iron belt is that they formed as the subduction zone environment changed at about 145 MA. You can see here that the slab between 145 and 100, the angle of the subducting slab increases. And that increase allows for, as the middle cartoon shows, it allows for back arc extension, and that creates normal faults. Normal faults are fluid conduits, and it also allows for back arc asthenospheric upwelling. And that's important because mantle upwelling can do several things. One, as the crust is thinning, it provides heat to drive convection within the overlying crust that is thinning as the slab angle increases. And it also results in juvenile mantle-derived magmas that move from the crust-mantle interface up to the upper crust and also erupting at the surface. In Jeremy's paper, I've now added the right side of his slide, and this is an area that my group and collaborators in Chile are now really starting to hone in on, which is if we think of subduction, if you look at the top, in terms of extension, sinistral transtension, and contraction, we're trying to understand how the tectonic regime controlled or played a determinative role in the formation of IOA, IOCG systems relative to porphyry systems. When you look at grade and tonnage, this is a plot showing you copper percent on the y-axis and tonnage on the x-axis. And the point that I want you to take away here is that all of the green boxes are porphyry copper, copper moly, copper gold deposits. These light green circles here on the lower left are porphyry gold deposits. And then the red circles are IOCG deposits. So you can see that IOCG deposits are almost identical in terms of the range of grade and tonnage as our porphyry systems. So now let me show you a few slides that highlight the different types of mineralization that we observe in iron oxide apatite or IOA deposits. So the picture on the top right, this is taken at the Alaco iron oxide apatite deposit in northern Chile. This is a deposit that actually formed in the Pliocene within the last few million years. And it has generated significant controversy since it was first described in a paper in 1961 in the Journal of Economic Geology. And the controversy has to do with, at the surface, everything you're looking at here between the dashed white lines is massive magnetite. Think of this as 98 to 99% magnetite with a really small amount of apatite and clinopyroxene and some diopside. So you're looking at what has been interpreted by some as a flow of an iron-rich liquid that we commonly think of as a silicate liquid. In this case, it would be an iron-rich liquid. You can see in the middle an example of iron oxide apatite mineralization at the Carmen deposit in the Chilean iron belt. And here what you're looking at massive magnetite here in the center to the bottom left of the photograph. And then you can see these veins that cross-cut pre-existing rock. And in this case, you can also see some large apatite crystals. Then we have massive magnetite that forms essentially dike-like bodies, and that's exemplified here at the Los Colorados IOA deposit in the Chilean iron belt. And what you can see is on the left side of the photograph, between these two dashed lines is a massive magnetite dike. And on the center part of the photograph, these two dashed lines are tracing a second massive magnetite dike. Each of these two dikes is 60 plus weight percent Fe. So they're almost pure magnetite with a very small amount of apatite and a small amount of actinolite. Now, in the case of Los Colorados, what you're also looking at here is the trace of the Los Colorados fault. And the mineralization at Los Colorados is hosted within that fault. The image on the left-hand side is a drill core from this massive magnetite dike on the western side or the left side of the photograph. And you can see, if you look carefully, it is almost entirely magnetite with a small amount of actinolite and an even smaller amount of apatite. If we categorize or characterize IOA deposits and give some general features, you can look here at the left, at the upper left of my screen. This is a schematic cross-section of the type locale, the Kiruna iron oxide apatite deposit in northern Sweden. And if you follow my cursor before you read the text, you can see that the ore body is contained within this fault. And these dashed lines at the top are the year at which the ore body existed at that surface, and now it has been mined out, and the mining is exclusively underground. If you look at the images on the bottom, Kiruna and every other iron oxide apatite deposit that we have studied and that we have read about in publications, it looks like this image on the lower left. Dominantly magnetite, in this case, a small amount of apatite, and there's often actinolite. These ore bodies are tens to thousands of millions of tons of ore. I've said magnetite dominates. The total iron concentration is similar to the amount of iron that we find in porphyry copper deposits. And iron oxide apatite deposits are economic because of the iron that they contain. They're sulfur poor relative to porphyry copper deposits. Magnetite has historically been reported as titanium poor, but I'll show you how that's not correct. Apatite can be enriched in rare earth elements. Historically, apatite was not mined for the purpose of extracting those rare earths, but that is now changing. Iron oxide apatite deposits are almost always associated spatially and temporally with igneous activity, and they're dominantly hosted within igneous rocks, forming in a subduction zone environment where mineralization is structurally controlled. So now let's switch gears and look at some general characteristics of iron oxide copper gold deposits. So this is a half drill core from the Candelaria IOCG deposit in Chile. This is the largest IOCG deposit in the Americas, the Western Hemisphere. And what you're looking at here is the top and the bottom of the drill core is massive magnetite. And that massive magnetite is cut by this vein of chalcopyrite, pyrite, additional magnetite, and actinolite, and some small amount of apatite. Now, when you look at the Candelaria deposit, we've been working on a drill core that extends from surface to slightly deeper than 1,100 meters in the deposit. And what we observed by doing very careful drill core logging, this was work that Irene Del Real did for her PhD dissertation, is that in the deeper parts of the Candelaria system, the mineralogy is dominated by magnetite and actinolite. And as the system shallows, the mineralogy is dominated by chalcopyrite, pyrite, and actinolite that cross-cut previously precipitated magnetite and actinolite and apatite. So there's a clear systematic change in mineralization from bottom to top in Candelaria. And based on our observations at every other IOCG deposit in the Andean margin and our reading of publications of IOCG deposits elsewhere, this seems to be a salient feature of these systems. So if we then characterize broadly IOCG deposits, if you look at the schematic cross-section on the left, this is a schematic cross-section for the Manto Verde IOCG deposit, also in the Chilean Iron Belt. And I've highlighted here the Manto Verde fault that was the fluid conduit for hypogene fluids moving from bottom to top. And as those fluids moved up along the Manto Verde fault, they were able to percolate into the hanging wall and footwall rocks, depending on porosity permeability relationships. And importantly, in all of the Andean IOCGs, we see an early generation of hematite, which is later reduced to magnetite. And the term that is used to describe that is musketovite. So early specular hematite that is subsequently reduced to magnetite, which is called musketovite. Now, IOCG deposits are also tens to thousands of millions of tons of ore. Magnetite is still the modally dominant mineral, but they're economic because of the copper that they contain, and the copper grades and tonnages of IOCG systems are consistent or essentially identical to the grades and tonnages of copper in porphyry deposits. What is notably different about IOCG systems and porphyry systems is that IOCG systems do not contain stockwork quartz veining, and IOCG systems are sulfur poor by several orders of magnitude relative to porphyry copper deposits. IOCGs are almost everywhere that we've looked coeval with igneous activity, but IOCGs are commonly hosted in both igneous and sedimentary rocks that form the hanging and footwall in these systems. They form in subduction zone and back arc spreading environments. And again, I highlight here, mineralization is structurally controlled. And then the bottom, the last bullet point here, is that these deposits are also commonly enriched in a large number of other elements: silver, cobalt, nickel, bismuth, selenium, tellurium, indium, uranium, light rare earths, fluorine, barium, molybdenum, that can attain ore grades in some of these deposits. Now, each of these two deposit types results from mass addition to pre-existing porous and permeable rocks. So if we look here at this table, on the left, I've got the three elements, copper, gold, and iron. And if we look at the first two, copper and gold, which are mined from IOCG systems, this is the grade for copper globally. It ranges from about 0.2 to 5% copper and about 0.1 to 1.4 grams per ton gold. And if we look at the crustal abundance of copper and the crustal abundance of gold, what IOCG deposits represent is the addition of 10 to 200 times more copper than we find in average continental crust, 20 to 300 times more gold than we find in average continental crust. And then if we look at iron, which is the economic commodity in iron oxide apatite deposits, they average 40 to 50 and greater % iron The average crustal abundance of iron is about 5%. So iron oxide apatite deposits represent an order of magnitude higher concentration of iron than we find in average continental crust. And you see that again if you look at these images on the bottom of the screen. So a question is, what process or processes resulted in the mass addition of copper and gold and iron in these deposits? So this is a cross-section from the Candelaria deposit in the Chilean Iron Belt, largest IOCG in the Americas. And what I'm highlighting here in blue, this is the Lar Fault, and the Lar Fault is interpreted to have been the fluid conduit for a hypogene fluid that moved from bottom to top. Now the dashed line, that outlines the main mineralized area. So what we're looking at here is mineralization within the dashed line that is hosted within these green rocks, or the color green here, which represents andesitic rocks that are older than the deposit that they host, older than the mineralization that they host. So when we look at this cross-section, we've got a hypogene fluid moving up the Lar Fault, and then porosity permeability relationships in the hanging wall and the footwall of this older andesitic volcanic rock. Those relations allow the fluid to move laterally and alter this andesite to form the mineral deposit. And we see that when we look in cross-section on the left side at the bottom, we have the lower andesite, we have an upper andesite, we then have a dacite that intruded above the lower andesite and below the upper andesite. The dacite is slightly younger than both. And if you look at the images on the right, the bottom right image is your typical unmineralized andesite. The middle image is what happened to that andesite that resulted in pervasive actinolite, biotite, potassium feldspar andesite that now hosts mineralization, right? So this is what I mean by mass addition. Nature started with your average run-of-the-mill andesite, and then hypogene fluids entered the system and altered and mineralized those original andesitic rocks. There are a range of styles of mineralization in IOCG systems, just as I described for IOA systems. And this is a mosaic here where I just want to highlight one of the minerals here in the center panel. You can see this mineral musketovite. Musketovite, again, is a salient feature of Andean IOCG deposits. And it is originally hematite reduced to magnetite. So it's specular hematite that is magnetic, now called musketovite. We can also see specularite veins that cut these systems. We see on the lower left chalcopyrite and pyrite. And then the upper left, we can again see at a thin section scale, this massive magnetite on top, massive magnetite on bottom, and it's cut by a veinlet that contains chalcopyrite, pyrite, actinolite, and additional magnetite. When we look at districts that contain multiple IOCG deposits, this is the Punta del Cobre iron oxide copper gold mining district in central northern Chile. And what I want to highlight is that there are a number of deposits currently being mined, and those are shown by the stars. So we've got deposits on the east side of the district, and we've got deposits on the west side of the district. Candelaria here is towards the south. And when you look at cross sections for each of these individual deposits, what Irene Del Real was able to show is that the deposits on the west side, if you look at each of these schematic cross sections, these are deposits where the ore fluid clearly percolated out away from the fault conduit into the surrounding footwall and hanging wall and mineralized pre-existing volcanic rock. If you look at the schematic cross sections on the right side, on the east side of the district, you can see that The majority of these deposits, mineralization is more restricted to the plane of the fault that was the ore fluid. So it's clear that fault structures are incredibly important as the fluid conduits for hypogene fluids. And it's also clear that porosity permeability of the hanging and footwall plays a determinant role in the style of mineralization, whether it's disseminated or fault bound. Other people have made observations in the Chilean iron belt, and this is a block diagram that is reported in these two upper papers on the lower left. And the point I want to make here is that I showed you a schematic cross-section a few minutes ago for the Manto Verde fault. That is now shown here as this MVF. And you can see there's the Manto Verde fault, and then there are other faults, all of which are essentially parallel to the main Atacama fault system that is parallel to the subduction trench in this area. And what I want to highlight is that when you look at some of the deposits, for example, here at Kelso, Kelso is an IOCG system. Copper makes it economic. When the mining company drilled at Kelso, and they drilled beneath the copper-rich IOCG mineralization, they drilled into iron-rich mineralization, dominated by magnetite. And this has been observed in almost every IOCG where drill core traverse the IOCG deposit and then continue to drill in the underlying rocks. And on the right-hand side is a schematic cross-section originally published by Dick Silito a couple of decades ago. And this version is a paper from Fernando Barra in 2017. And it's a busy diagram, but here's all I want you to see. All of the systems that have been studied in the Andean margin, they are dominated by magnetite at depth, and they transition to chalcopyrite plus magnetite as the system gets shallower. It seems to be a fundamental characteristic of every IOCG deposit. As you drill deep, you drill through the copper-rich IOCG mineralization into underlying copper-sulfur poor, magnetite-dominated mineralization. And this has been hypothesized to indicate that this is a transition from iron oxide apatite mineralization at depth to iron oxide copper gold mineralization closer to the surface. So let's look at IOAs. We've spent a lot of time looking at IOAs under the microscope, the SEM, the electron microprobe, and the TEM. And this is an example of what we observe in magnetite in every single IOA system that we've looked at. If you look at the left side of the screen, this is a backscattered electron image of magnetite, and you can see that it's relatively boring, although if you look carefully, you can see that the outer margin of magnetite is less inclusion rich than the core of magnetite. If we then look at iron again, relatively boring, magnesium, relatively boring, but titanium, this is like the Van Gogh of IOA deposits, and nobody can throw tomato paste on this. When you look at titanium maps of magnetite in every single one of these systems, there is always a titanium-rich core of magnetite that is overgrown by a mantle that contains less titanium. And what I want you to see here, and I'm drawing around this, is this lighter blue color represents lesser amount of titanium than the dark blue. And you can see that if you look at this core, there's a lot of the lighter blue within here. So one interpretation is that the core of this magnetite formed at, let's say, time A, and then the magnetite grain was exposed or re-equilibrated with an aqueous fluid that dissolved and reprecipitated magnetite and essentially ate its way into this original magnetite core. When we look at the data from these systems, I'm going to highlight what we see at El Laco. So here is again that photograph top left for El Laco. In the middle, I've got a drill core that extends from surface to slightly deeper than 200 meters. And this is a drill core from one of the ore bodies referred to or called Laco Norte. This is work that Jose Tomas Oval did for his PhD dissertation with Martin Reich at the University of Chile. And what I want you to see is that Jose Tomas has sketched out in the center here how the style of mineralization changes from surface to 200 meters. And then what Jose Tomas did was to very carefully make observations of magnetite textures from the surface to the deepest part of the drill core. And what he also did is measured the abundance, the concentration of titanium in the magnetite. That is shown here just to the right of this colored drill core. And what you can see, this is what I want you to see. If you look at the surface, this is characteristic of what you would see. You see magnetite that has been altered to hematite, that has been altered to goethite. It's just characteristic of the surface mineralogy at El Laco and many other IOA deposits. But when you start to look at magnetite as you get deeper, you lose goethite. It's dominated by magnetite, some of which has been altered to hematite. And this pattern, as you go to depth, what we see are multiple generations of magnetite indicating multiple pulses of ore fluid that move through the system from bottom to top. And I'll highlight that if you look at the bottom right image here, magnetite in the deepest parts of El Laco, it is not titanium poor, as many people have reported. In fact, when you look at magnetite, you can see these ilmenite exsolution lamellae, and the only way for that to happen is that the original magnetite contained a high enough concentration of titanium that during cooling and oxidation, it exsolved initially ulvospinel that then crystallizes to ilmenite. So the takeaway here is that when you look at drill core in IOA systems, there are multiple generations of magnetite recorded in the rock. Now, I've added on this slide how the composition of the magnetite from depth to surface changes. So if we look at the plot on the right side of the screen, I've got on the y-axis here aluminum plus manganese, and on the x-axis titanium plus vanadium. The gray arrow here is for this drill core on the left side of the screen. And what you can see is that the arrow where it starts here that I'm circling around, that is the drill core at 200 meters. And the arrow at its tip down here where we see these purple diamonds, that is the surface. And what the gray arrow shows you is that there is a systematic decrease in the concentrations of all minor and trace elements in magnetite from depth to surface. Now, let me repeat that. There's a systematic decrease in the minor and trace element concentrations of magnetite from depth to surface. And we see this everywhere we've looked. We've looked now at magnetite in IOA deposits in Chile, the USA, Iran, Australia, Sweden, you name it, we've looked at it. And if you have some that we haven't looked at, send me an email and we'll look at it. And we see the same exact trend in every system. So this is a busy diagram that Gisela Palma published in 2020 in Ore Geology Reviews. And all I want you to see is that in every single system where we've analyzed magnetite in drill core, where we have really good spatial control of surface mineralization to the deepest mineralization, the deep samples are trace element rich and the shallow samples are trace element poor. It is systematic and it is reproduced at every single deposit. When you put that together and start to look at the temperatures at which magnetite crystallized, we have done a systematic analysis of published temperatures from stable isotope thermometers, fluid inclusion studies, and now one can use a magnesium in magnetite thermometer to estimate the temperature at which magnetite crystallized. And in the case of El Laco, what I'm showing here is when you look at the temperature at which magnetite crystallized in the shallow, the intermediate, and the deep zone, you can see that the average temperature is about the same, but the range of temperatures increases from depth to surface. And we see this everywhere. So now we're looking at other IOA deposits in the Chilean Iron Belt. And what we've also done here is we have essentially, total brain fart here, looking for the word. We have plotted these as a function of depth. So El Laco is an IOA deposit that outcrops at surface. The y-axis here is increasing depth. And what you can see is that there's variability as a function of depth for the average magnetite temperature. And then there is a range of magnetite temperatures that extend from about 300 degrees to as high as 1,000 degrees. Now, remember earlier I showed you that there are multiple types, textures, and compositions of magnetite in each of these systems as a function of depth. Gisela also did a systematic study of the textures of magnetite in these iron oxide apatite deposits. And on the right side of the screen are her artistic renderings of the different textures that she observes in all of the systems that she studied in the Chilean Iron Belt. And we can use that to reconstruct a depth profile that relates to the textures we see on the right side of the screen. So on the left side of the screen, if we have surface at top and with depth we have increasing pressure, we can see that in IOA deposits such as A that form at deeper levels of the upper crust, they ubiquitously contain magnetite with ilmenite exsolution lamellae. And then as you move from deep levels to shallow levels, what Gisela was able to document is that these textures are systematically changing, and we suggest they're systematically changing because of the pressure and the temperature at which the fluid was precipitating the magnetite. So now let's switch gears again and look at IOCG deposits. This is from a paper that Maria Alejandra Rodriguez Mustafa published in the Journal of Economic Geology. And this is a study that she did on the Mina Justa IOCG deposit in Peru. These are representative BSE images. And all I want you to do is, if you look at each of the panels, what you see are multiple generations of magnetite. Oh, excuse me, this is not Mina Justa, this is Candelaria, scratch that. You see multiple generations of magnetite, and in the deeper levels of Candelaria, you see magnetite that coexists with ilmenite. And the most plausible explanation for this coexistence is that the original crystal that precipitated, or the original mineral that precipitated, was a titanium-rich magnetite that underwent oxy-exsolution, granular oxy-exsolution, to exsolve the titanium that now exists as ilmenite. If we look at Candelaria, I showed these images again. Remember, what I wanted you to take away here is that in the shallow levels of the system, we have chalcopyrite, pyrite, actinolite, magnetite, and that is cutting earlier or older massive magnetite. And then as we go to deeper levels of the system, we lose copper iron sulfides, and the system transitions to almost entirely magnetite with lesser actinolite. Now, we've spent a lot of time trying to fingerprint the source of the fluids that precipitated the ore minerals in these systems. And one of the systems that we've used is to look at iron isotopes and oxygen isotopes. And when you look at the diagram here, all that's really important is to look at the dashed lines. And what the dashed lines tell you here on the top right is that if you give me a sample of magnetite from any unaltered igneous rock on the planet Earth, and I measure the iron and oxygen isotopes, it will plot in this box. And if you give me any sample of magnetite that precipitated from a silicate magma-derived magmatic hydrothermal fluid, it will plot within this slightly larger box in iron versus oxygen isotope space. On the left side of the diagram, we can see that as an original igneous or magmatic hydrothermal magnetite is altered at lower temperatures than it originally crystallized by a hydrothermal aqueous fluid, that shifts the oxygen isotope values shifts the oxygen isotopes to lower values. And what we have found, and other groups have reported this as well, Valentin Troll at Uppsala just had a review paper out last year where they reported exactly the same observations and interpretations, is that when we plot all of the data for El Laco, all of the data for all of the deposits in the Chilean Iron Belt, the data for all of the systems in Sweden, all of the data for Iran, all of the data for the Missouri deposits, look where they plot. All of the data are telling us that the iron and oxygen was sourced from a silicate magma. And when we have lighter oxygen isotope values, as are shown here for El Laco, that represents post-mineralization alteration. We've also recently started using triple oxygen isotopes. So conventional oxygen isotopes is the ratio of 18 to 16. Now we're measuring oxygen 17, and the diagram is busy, but I just want to highlight here on the right side of the diagram, purely igneous and magmatic hydrothermal magnetite would plot inside this rectangle. The smaller rectangle on the right represents mantle values for cap delta 17 oxygen versus delta 18O. And what the 17 oxygen isotope data allow us to do is they're allowing us to see the effect of post-mineralization alteration of magmatic hydrothermal and igneous isotopic signatures by external fluids such as meteoric or basinal brines. And we can see that if we look at the data here, and the star at the bottom represents magnetite in equilibrium with fluids that exchanged oxygen with evaporites. So this is not a mixing line happening during mineralization. It's telling us something about the fluids that altered the deposits after mineralization. And again, on the right, these are data for districts around the world. We also can look at these data and back out that goethite I showed you earlier. And if I just highlight on the left-hand side, when you look at hydrogen versus water content of magnetite, you can see that as you increase, or we can observe an increase in goethite, we see hydrogen isotopes get lighter and water contents increase. And this also correlates with lighter values of cap delta 17. We've looked at hydrogen isotopes of magnetite. The hydrogen is consistent with mantle. We've looked at hydrogen isotopes of actinolite. Hydrogen isotopes are consistent with mantle. We have measured the collective this is data from one of Irene Del Real's papers. We have measured sulfur isotopes in sulfides, in Candelaria, and other IOCG systems. And the box here, top left, this is on the y-axis, the ratio of selenium to sulfur. And on the x-axis is this classic delta 34 sulfur, the ratio of 34 to 32 sulfur relative to a standard. And what we see is that a majority of the data plot within the known range for mantle-derived magmatic fluid sources. And we can see a mixing trend for some of the sulfides that are the result of this late stage incursion of basinal seawater derived fluids. But these are post-mineralization. We've looked at pyrite. The plot on the left is cobalt versus nickel in pyrite. And then the contours here are cobalt nickel ratios of 10, 1, and 0.1. And the importance of cobalt nickel ratios in pyrite is that high cobalt nickel ratios are consistent with the ore fluid from which pyrite precipitated. That ore fluid was sourced from a intermediate to slightly mafic silicate magma. We see the same thing in every deposit we've looked at. So now I'm showing you, this is the depth, the drill core for the Candelaria system. So we've got 0 down to more than 1,000 meters. And what I'm showing you here is this gray area represents iron grade. The center here in red represents copper grade. And the gold or yellow here on the right represents gold grade. And what we see when we look at all of the IOCG systems where we have drill core that traverse the entire IOCG system into the underlying rock that is itself mineralized and dominated by magnetite, we see systematically the effects of these reactions. So we know very well that iron is extremely soluble in hydrothermal aqueous fluids as this complex FeCl2. And as iron that is in a hydrothermal aqueous fluid, as that hydrothermal aqueous fluid reacts with rock as it's percolating through that rock in the hanging wall and the footwall or within the fault, that FeCl2 is destabilized and crystallizes magnetite. All right, so we know very well how iron can be introduced into these systems. We also know that in the IOCG systems where we have evidence for very early hematite, fluids that percolate through that system carry hydrogen with them and can react with that hematite to reduce it to magnetite, which we call musketovite. So these chemical reactions are consistent with what we see in the systems. And I want to make a point here. Remember that iron oxide apatite deposits, they're fundamentally magnetite deposits. The amount of apatite in these deposits, it is poquito, poquito, poquito. I mean, there is a whiff of apatite in some of these systems. And that's really important because a lot of people advocate models that require lots of apatite, and it's just not there. We have done modeling in a paper here that I reference on the lower left. Martin Reich is first author. And what Martin did here is to thermodynamically model the solubility of iron in aqueous fluids as this iron chloride complex. And all you need to take away here is that the y-axis is the molality, the moles of iron per kilogram of fluid. The x-axis is temperature, and each of these contours is constant pressure. And what the data reveal is that at high pressure, a fluid can dissolve and transport an order of magnitude more iron than the same fluid at low pressure. So the bottom here legend shows you pressures decreasing from 200 to 60 MPa. So that's a depth range of something on the order of 8 kilometers down to about 2 kilometers. And fluids that evolve from silicate magmas, they will, as a function of the depth at which they evolve, that dictates the lithostatic pressure on top of that magmatic system. And that dictates, for a given chlorine concentration, how much iron the fluid can transport. And if you then translate these into the precipitation of magnetite, you can see that on the x-axis, we still have temperature, where we're going from hot on the left to cool on the right. And what we can see again is that as a function of pressure, pressure will control the temperature at which magnetite precipitates. And the data indicate that the precipitation of magnetite from an aqueous hydrothermal fluid is enhanced by rapid decompression. So now let's look just briefly at some chemical reactions that explain iron oxide copper gold mineralization. I showed you earlier this drill core, massive magnetite that clearly predates this vein of chalcopyrite plus pyrite plus some additional magnetite and actinolite and apatite. So we know we have massive magnetite, and then superimposed upon that, we have chalcopyrite and pyrite. And if you look at the reactions here on the bottom, that is easily explained by an earlier generation of magnetite that precipitated as I talked about here. And then it is overprinted by chalcopyrite, and that's explained simply by the reaction here in the middle. Copper is primarily complexed and transported as a copper chloride in aqueous fluids. If that copper chloride in the fluid moving through the vein, and that vein is cutting massive magnetite, it will react with massive magnetite, it will destabilize massive magnetite, copper comes out of solution, and the copper and iron and sulfur precipitate as chalcopyrite. So it's really a simple process that we can explain with well-established experimental and thermodynamic data. And then the second reaction here explains how an aqueous fluid reacts with that magnetite to produce pyrite. And again, if there's any specular hematite, that fluid will reduce the hematite to musketovite, which is magnetic specularite. So the chemistry seems relatively straightforward. So now I filled out the diagram in the center of the slide. Here's what we observe at every one of the deposits we've looked at. And again, it's like an ice cream parlor. There are different flavors, but fundamentally, they're ice cream. So if we look at the center here, in the lower or deeper parts of these systems, they are magnetite rich, copper iron sulfide poor. As the system transitions from deep to shallow, you can see here, this is an example from Candelaria. This is why Candelaria is economic, because it's got these high copper grades that exceed in some parts of the system 1 weight% copper. And all of that copper, notice that it's only in the upper part of the system. And then if we look at the right-hand side here, we can see that there's also significant gold, and gold correlates perfectly with copper because gold is contained within chalcopyrite. So we see this transition from deeper magnetite-dominated mineralization to shallower veins of copper iron sulfide. And it seems entirely consistent with this schematic diagram on the left, where each of these systems that we've explored with drill core that traverse the entire system into the underlying rocks, what you can expect is if there's IOCG mineralization at or near the surface, beneath that IOCG mineralization, there will be significant massive magnetite. And that should be helpful for exploration because that leads to a very large magnetic or gravity signal when you're doing regional aerial surveys. Oh, and then this one, I'm getting close to the end here, and I know there are questions, and I don't want to cut short on time, but if you only focus again at the middle and the right, I highlighted earlier that we know thermodynamically the PT conditions under which magnetite precipitates. Well, when you look at IOCG systems and you can see the copper and gold mineralization that is significant in the upper portions of these systems, that's telling us that it's a temperature effect. And if we look at the two plots on the right from Anthony Williams Jones group at McGill University, what you're looking at here in A and B is the amount of molybdenite and chalcopyrite that precipitate from an aqueous fluid as it cools from high temperature on the left to low temperature on the right. And what you can see is depending on the FO2, FS2 buffer, pyrite, hematite, magnetite, or pyrite, pyrrhotite, magnetite, you can see that chalcopyrite is perfectly stable, dissolved in a fluid as copper chloride until that fluid cools to temperatures below 600 degrees. And then boom, all of a sudden, now we have a fluid carrying copper chloride. It's moving through rocks that previously were mineralized with massive magnetite. The temperature is in the sweet spot. That copper chloride sees magnetite, copper chloride plus magnetite, chalcopyrite. Iron plus H2S plus magnetite, pyrite. It all makes sense, and it's consistent with all of the experimental and thermodynamic data for these systems generated over decades. So I'm going to jump ahead here, and I'm going to tell you how we envision these systems forming. And we think it's really simple. We think it's essentially nearly identical to how porphyry systems form, except IOCGs and IOAs do not have that stockwork veining. And we know that quartz stockwork veining in porphyry systems is the result of an extreme pressure change during the explosive release of the ore fluids from the magma chamber. In IOCG systems and IOA systems, what we think is happening is that the ore fluid is sourced from a magma that has less silica than the magmas that give rise to porphyry fluids. So porphyry fluids are typically intermediate to more evolved chemically, higher SiO2, higher Na2O, higher K2O, less iron. Whereas in IOCG and IOA systems, we believe in our model, but we propose a model where we have a slightly intermediate to mafic magma. And the key difference is that these magmas, remember, magmas follow the path of least resistance. So when we're looking at, for example, in the Andes, the Atacama fault system, that's a basement penetrating fault system. So during the change in subduction from 140 to 100 MA, when subduction is going from shallow to steep, and we have back arc extension, and we have mantle upwelling, right? We have the evolution of the Atacama fault system, and these magmas will move into the upper crust where they will pond and release their fluids. And those fluids, they don't explosively evolve from the magma chamber. It's more of a quiescent release where the fluids are able to evolve from their source magma into these overlying faults that the magmas themselves have taken advantage of. And because the fluids are coming from intermediate to more mafic magmas, that means that the fluid will have a much lower concentration of dissolved silica, and as a result, will not precipitate quartz as a major feature of these systems. So as a function of time, what we propose happens is that the system evolves from an earlier, hotter system where we have dominantly magnetite mineralization. And then as a function of time, what we see from left to right is we see a sequence of fluids evolving from their source magma. We know that that magma, it can change in composition and temperature owing to underplating and injection of hotter magmas over its lifetime. And when you look at the mineralization within the deposits, the style of mineralization, fault bound versus disseminated in the wall rocks, the hanging and footwall of these faults, that simply represents porosity permeability. And the reason that the systems transition from magnetite at depth to copper iron sulfides at more shallow levels, that's dictated by the fluid cooling path from depth to surface. And I think I'm going to stop there, Jess, and take questions.